Hey, let's begin with the sequences and series. So, in this particular lecture, we're going to specifically talk about the convergence of sequences. The term convergence of sequence is basically related to boundness of the sequences. So, what is the boundness indicates? There are bounded below sequences and bounded above sequences, which we will discuss in this lecture. So now, and we also see about the monotonicity of the sequences, and then we compare both these terms of the sequences, and then we get that it is a convergence or divergent or oscillatory sequences. So let's talk about this convergence. So convergence, if limit n approaches to infinity, and an is sequences as n approaches to infinity, if we get our nth term, that is infinite term, as n approaches to infinity, if it is equals to finite number, then we will get that our given sequences is convergent sequences. And as we all know, so it must be bounded. We will discuss in this lecture a particular specific theorem about it. So let's begin with the introduction part of the chapter.
So let's look at the what is sequence. A sequence is a function whose domain is the set n of all natural numbers, whereas the range may be any set s. Bounded above sequence. A sequence is said to be bounded above if there exists a real number k such that an is a sequence which is always less than or equal to k. So let's see bounded below sequence. A sequence is said to be bounded below if there exists a real number such that an is always greater than k of that real number for all n belongs to natural numbers. So let's look at the graph of it. For bounded above, we have seen that a sequence is said to be bounded above. So if there exists a k, so k is this particular x-axis which is 0, 0, and we have to know that an should always be less than that particular above bounded. So here bounded above is this is the 0, 0 point. So in the next case, bounded below, which means it should be bounded below, and upper side it may or may not be bounded above. So that's the so an should always be greater than for some constant k, real number k, for all n belongs to natural numbers. So sequence is defined by an here, and that's the cases of the both the sequence bounded above and bounded below. Now let's look at the what is a bounded sequence. A sequence is said to be bounded sequence when it is both bounded below and above. A sequence an is bounded if there exist two real numbers k and k such that k is always less than or equals to large capital K, such that k an should lies between both of these k, smaller k and capital K for all values of n belongs to natural numbers. So this is the example of bounded. So if this is the above k, which is capital K, and this is and the minus m represent the small k for all every value of n. So this function or sequence is known to be as bounded sequence. Now let's look at the unbounded sequence. If there exists no real number m such that an modulus is always less than or equals to m for all n belongs to natural numbers, then the sequence an is said to be unbounded. Now it means an must not be in the interval for unbounded. Here, if either of the case is not matched, like it is not bounded above, either it must be bounded below, but it should not be bounded above any either of them, then it must be unbounded sequence. So that's the idea about the unbounded sequence. So let's look at the here an modulus indicates that it must be less than or equals to m, indicates an should always lies between, so it should not be lie between actually in this m. So if any of the a value is not true, if any of the bounded above or bounded below is not uh, falls into it, then that particular sequence must be unbounded sequence. Now let's look at some examples. The sequence an defined by an is equals to 1 by n is bounded, since for every value of n natural numbers we have uh, first we have an equals to 1 plus and a2 is equals to 1 by 2 up to so on. We will see that at the n approaches to infinity we will get just maximum value we will get is either 0 and minimum is 0 as n approaches to infinity, and maximum is as n approaches to 1. So it is bounded above and bounded below, so it is a bounded sequence. So an is equal to n, so it is a bounded below because we cannot go below 0 for any n belongs to natural numbers, but we can go up to infinity and we can put n equals to infinity, which we will get. It's not bounded above, so it is only bounded below for any value of n, so it cannot take negative values, so it cannot go up to infinity natural numbers. So the sequence minus 1 whole raised to power n is bounded since an takes either value minus 1 or plus 1. So we can say that a lies between minus 1 and 1. So it is bounded. But the sequence minus 1 whole raised to power n into n is neither bounded below nor bounded above. And it may be lie between minus infinity to plus infinity, because if n approaches to infinity and if infinity is positive even, then we will get plus infinity. If infinity is odd, either of its sign, so we will get minus infinity. So we don't define it as, so it must be lie between minus infinity to infinity. Now let's look at what is a monotonic sequence. A sequence n is said to be monotonical increasing sequence if a n plus 1 is always greater than equals to a n for all n belongs to natural numbers. So that is, this is example, a1 is always less than or equals to a2 and up to so on up to n plus 1 term. A sequence an is said to be monotonically decreasing if an plus 1 is always less than or equals to an. That is, a1 should always be greater than or equals to a2 and a2 should always be greater than up to so on. A sequence an is said to be strictly monotonically decreasing if it is given that an plus 1 is always greater than an. So it is not should not be equals to any of the values. So if we will say that every value of sequence is equals, then it must be constant. So that's not the strictly monotonical decreasing or increasing function. So it must be constant lie between any of the sequence term. So a sequence an is said to be strictly monotonically increasing if an plus 1 is always less than an for all net n belongs to natural. Now let's look at the convergent, divergent and oscillatory sequence. Convergence sequence is said to be a sequence is said to be convergent if limit n approaches to infinity an is finite. For example, consider the sequence 1 by 2, 1 by 2 square and 1 by 2 cube up to so on up to 1 raised to power 1 by 2 raised to power n. Here an is 1 upon 2 raised to power n, and if limit n approaches to infinity an equals to limit n approaches to infinity 1 upon 2 raised to power n is equal to 0. As n approaches to infinity, the denominator will becomes infinity, so 1 by infinity, which is equals to 0, which is finite. So the sequence an is convergent. So if divergent sequence an is said to be divergent if limit n approaches to infinity an is not finite. That is, limit n approaches to infinity an equals to minus infinity or infinity. For example, consider the sequence n square. Here if n approaches to infinity, we will get an equals to limit an equals to infinity. So this sequence is known to be divergent. Now let's look at the third one, which is oscillative sequence. If a sequence an neither converges to finite number nor diverges to minus infinity to plus infinity, it is known as oscillative sequence. So there are of two types. A bounded sequence which does not converge is said to be oscillate finitely, and for example, an unbounded sequence which does not diverge is said to be oscillate infinitely. So let's look at the examples. Consider the sequence minus 1 whole raised to power n into n. It is known as unbounded because as n approaches to infinity, so it will goes to plus infinity, either minus infinity, depending on the value of a infinity, which is if it is either odd or it is either even. So if it is even, then it must be goes to plus infinity. If it is odd, so if there is we will get the odd as the n approaches infinity as 2 into infinity plus 1, we will get odd of n's terms, so it will becomes minus. So it is not diverging, but it is oscillative sequence, because here we have unbounded sequence which does not diverge is said to be oscillating infinitely, because it is one side it go plus infinity and other side it go minus infinity, and to the next term it goes again plus infinity. Now bounded sequence which does not converge is said to be oscillate finitely. So these are the three types of sequence we have seen. Now let's look at the convergence of monotonic sequence. Let's look at the theorem. Theorem 1. The necessity and sufficient condition for the convergence of a monotonic sequence that it is bounded. Theorem 2. If a monotonical increasing sequence is not bounded above, it diverges to plus infinity. And theorem 3. If a monotonic decreasing sequence is not bounded below, it diverges to minus infinity. So if simply say that, so if it is monotonically increasing function and it is not bounded above, so it will definitely goes to plus infinity as it is not bounded above. So if it is decreasing sequence and it's not bounded below, it must be diverges to minus infinity. And the third condition is commutative law, which is a and bn are two convergent sequence, then an plus bn is also convergent. And the fifth one is a and bn are two convergent sequence, so the limit an is a and limit bn is b, then the multiplication of both is also convergent and is converges to ab. So a sequence an upon bn is also convergence and converges to a.
I hope you enjoy my content, and please don't forget to like, subscribe to my channel. Till then, keep learning and keep exploring. And as always, free to email me at dsvfx6789@gmail.com.